we can start. Awesome. Hello, everyone, and welcome to the CosKASI ECR seminar. It's a great pleasure for me to introduce our speaker, Johannes Eskilt. Johannes did his master's degree at Imperial College London and now currently doing a PhD degree at the University of Oslo. And today, Johannes will be talking about improved constraints on cosmic birefringence. Johannes, take it away.
Great, thank you so much. Thank you for inviting me for this seminar talk. I'm going to talk about cosmic birefringence, which is a project I am very passionate about. And it's pretty much the main project of my PhD. It wasn't supposed to be, but it's very promising stuff. And so, yeah, I'm almost working on this full time now. Yes. So, as you all know, we don't really know what the universe is made out of. We know that the universe is made out of dark energy, it's made out of dark matter, and it's made out of normal matter. And so what I'm going to be talking a lot about is what these things could be. And one of the things that these could be are axioms. Axioms are a potential particle that could explain all these things. And yeah, so I'll be talking about sorry, give me 2 seconds here. So yeah, so axioms are hypothetical particles that could couple to electromagnetism. And so we all know that electromagnetism looks like this. And then when you couple them to a field phi, for example, which is an axion-like particle, it can then change how particles, how photons behave. And so this changes how the left and circle polarization of light, they move at different phase velocities. And so that if the field phi here, for example, changes over time, that means that there will be an effective rotation of the linear polarization of light. And so, and so the linear polarization of light will then rotate as the light propagates throughout space. And so you can see that that's written like in this equation, where beta here is how much the light rotates, or the polarization of light rotates as it propagates through space. And so that's given by this coupling constant times how much the field moves from it's emitted to it's observed today. And yeah, so it only depends on how much the field phi changes. And this is also a parity violating effect. And so it will be very interesting to observe something like this because we don't have many parity violating effects in physics right now. We don't have the weak nuclear force. And just to talk a bit about how these, what kind of particles we could detect these ways. So we know that Hubble friction causes ultralight fields to move very slowly. And so if you have an axion-like field that has the mass between the Hubble constant today and the Hubble constant of the CMB, then you would expect that the value of the field when emitted to be non-zero, but today it would be 0, and so there will be a delta phi that's non-zero here. And so the beta you would then measure today, how much the polarization rotates, would then be proportional to the emission value of that field. And so if you had such an ultralight axion-like field in this mass range here, then you would expect to see an isotropic signal that linear polarization of polarized light from all parts of the sky will be rotated by the same amount. And this effect is called cosmic birefringence. And so let me then just quickly mention what birefringence is. So we have something called birefringent materials, and those are materials that causes linearly polarized light to rotate. And you can also create the same effect by using magnetic fields, which is called the Faraday rotation. So you can see this in this example here. If you put in linearly polarized light like this, that moves parallel to magnetic field, then the linear polarization will then rotate. as it goes through this magnetic field. And so this is what birefringence is. So we're wondering then, what if a vacuum is birefringent on the cosmological scale? That will be cosmic birefringence. Yes, so we then, if you want to look at this on a cosmological scale, we need to look at not just the oldest light in the universe, which is the CMB. The CMB is also the oldest polarized light in the universe. It's linearly polarized. And so the CMB will be a great source to see if vacuum is birefringent. And yeah, so CMB will be the best way to look at cosmic birefringent, because you can then see if these linearly polarized light here, as you can see as the black lines here, have rotated or not, as the light had propagated for 14 billion years. So yeah, and so that is the project that I have been working on, and that is the Cosmic Birefringence project. So you can then look at, so shortly said, you can look at the E modes of the CMB, see if they have rotated or not into something that looks more like B modes as the light has propagated for 14 billion years. Yes, and spoiler alert, we think we are measuring this, or we hope so at least. And with the newest work with Ichiro Komatsu, we find this angle to be 0.34 plus minus 0.09, which is and we're at the 3.6 sigma level, which is something we are very excited about. And I will now talk about how we measure this. So how do we measure isotropic cosmic birefringence? We do this by looking at the Q and U Stokes parameter of the CMB light. But the Q and U Stokes parameters are coordinate dependent, and so we transform them into something that's coordinate independent, so-called E modes and B modes. And you can see how they look like here. I should also mention that these E and B modes are not, they have nothing to do with electric and magnetic fields. They're just the lines that comes from them looks like magnetic and electric fields, in the fact that you have like curl-free and gradient-free vector fields. Yeah. So negative E modes looks like this, positive E modes looks like this, and then have B modes that look like this. And it's also important to mention that the E modes are parity even. So if you put these in a mirror or look at this in a mirror, they look the same. But for B modes, if you look at them in a mirror, they switch signs. So negative B modes becomes a positive B mode. Yes. So the amount of E and B modes, we quantify them by looking at power spectra in harmonic space. And in harmonic space, so this is basically a Fourier transformation over a sphere. And we then get power spectrums like this, that tells us how much E and B modes we have over different scales. So we do this in multiple space, or spherical harmonic space, which gives us different multiples. So the further you go on the x-axis here, high in multiples, the smaller scales you are looking at. And we know very well how the EE power spectrum of the CMB looks like. And we have also tried our best to find the BB power spectrum of the CMB, because if you can find intrinsic BB power spectrum of the CMB, you can then you have them like proven inflation, or found very, very good evidence for inflation. So that's what the entire CMB field is looking for, is this power spectrum. And then the lambda CDM also predicts a TE power spectrum, but it does not predict an EB or TB power spectrum at all. And these are the things that I will be talking about today, because parity symmetry says that the EB and the TB power spectrum should be 0, as I mentioned earlier, with the fact that B modes are, they switch signs on the parity. And the lambda CDM says that parity should not be violated. But if you do have cosmic birefringence, then you have parity violation. You should see non-zero EB and TB. And so this whole analysis is all about measuring the EB of the, measuring the EB to see if we can find this parity violating effect. So this is how we measure cosmic birefringence, by looking at the CMB. If we had perfect instruments and no galactic foreground, then this analysis will be very, very simple. You take the E and B modes of the CMB, and then you rotate them by rotation matrix by the cosmic birefringence angle, and you get the observed E and B modes. This is how it looks like for our satellites and our telescopes today. And if you can then take this equation, and then you can derive this this equation down here pretty simply. And we can then easily calculate the observed EB power spectrum today. And we know very well that there's a lot of EE from the CMB. There's almost nothing, no BB from CMB. Yeah, and so this equation will be very simple to solve for beta here. You also get the this equation also needs the intrinsic EB of the CMB. So the intrinsic EB that came from this CMB when it was created. But lambda CDM doesn't predict this to be there at all. So we just set this to 0 in our analysis. But if that is non-zero, then that will also be like equally cool and important. Yes, but the world is not perfect, and there are two main problems with doing this kind of analysis. And one of them is that instruments are not perfect. There's a miscalibration angle. So if you have an instrument that's trying to measure this linear polarization here, so this is the actual linear polarization of an incoming light, but your instrument measures this line instead. And so it's off by some alpha here, which is the miscalibration angle. It's and all instruments have a miscalibration angle because no instruments are perfect. So they will always be off by some alpha here. But this alpha is perfectly degenerate with beta, the cosmic birefringence angle. And so that if you only look at the CMB, and that is a huge problem with these kind of analysis. And the other problem is that there's galactic foreground. So we are interested in the CMB, which looks like this, but instead our satellites and telescopes, they see this instead. So you can see in the middle here, you can see a very strong signal, which comes from dust contamination and synchrotron radiation. And this is also polarized because our entire analysis is all about polarization. And so we need to find a way to remove it or use it to our advantage. So just to mention a bit more about the miscalibration angles. So people have looked for cosmic birefringence before, but as I mentioned, the miscalibration angle, which is different for each experiment and each detector, is perfectly degenerate with the cosmic birefringence angle, which is the same for all experiments. And so whenever earlier experiments have been trying to measure it, they have always only been able to measure the sum of the two. And you can see that pretty much all experiments have done this, and they have measured very different values for this. For example, SPT here have a 15 sigma non-zero alpha plus beta. But these values don't really tell us much at all. They mostly tell us what their alpha is, but not beta. Because there's no way for them to break this degeneracy between alpha and beta. And we are only interested in beta here. And so these measurements don't tell us what is the cosmic birefringence angle, only the sum of that miscalibration angle and the cosmic birefringence angle. But then a new method was developed that was created to break this degeneracy between miscalibration angle and cosmic birefringence angle. And the assumption is pretty simple. The foreground is relatively close to us. The light from our galaxy is 100,000 light years away, while the CMB is almost 14 billion light years away. And so the photons from the CMB has traveled so much longer and further than the foreground photons. And so that's the main assumption here. The CMB photons are then the linear polarization of the CMB photons have been rotated by the miscalibration angle plus the cosmic birefringence angle, while the light from the foreground has only been rotated by the miscalibration angle because these photons haven't moved far enough to be rotated by cosmic birefringence. And this ends becoming what we observed today, the observed E modes and the observed B modes. And then you can take this equation and you can do some math and you can derive this equation here. And this is the main big equation that we use in our analysis here. So you have the observed quantities. You just take them from your satellite experiment with everything, with the foreground, with the CMB, with everything. You have the observed EB, you have the observed EE, the observed EB, and then in addition, we also know very well what the EE of the CMB is, and yeah, there's not that much BB, and so we have all the quantities that we need here in order to do a Markov chain Monte Carlo analysis to measure alpha and to measure beta. And in addition, you have this bottom line here. As I mentioned, we set EB of the CB to 0. But a big problem here is then the EB of the foreground, because this is the intrinsic EB correlations of the foreground, which hasn't really been measured, so it must be very, very weak. Yeah, and we have been spending a lot of time trying to figure out what this is, and we're pretty confident we understand this much better now. Yeah, so I will be talking about this later. Yes, so just to show you how this works more, this analysis was done by Minami et al. On simulations. So if you look at a frequency of the sky where there's little dust contamination and a lot of CMB signal, you can then, with this method, constrain alpha plus beta very well, as you can see by this line here. It's very well constrained, because as I mentioned, if you only look at a CMB, you cannot break the degeneracy between miscalibration angles and cosmic birefringence angle. But on the other hand, if you look at frequencies where there's a lot of dust contamination, a very, very strong dust signal, and very little, or relatively little CMB signals, then you can only constrain alpha pretty well. But if you then combine these two, and you can constrain alpha well, and you can constrain alpha plus beta well, you can also constrain beta. And that is how this analysis works. We look at many, many different frequencies, and we do cross power spectrums between them, and we're able to measure all the miscalibration angles for all the different frequencies and one cosmic birefringence angle. And this is how we do this. So I remember 6 weeks after I started my PhD, this paper came out by Minami and Komatsu, and they had applied this method that they had validated using the simulations I showed. And then, yeah, then they applied it to real data. They applied it to the Planck 2018 data, and they found a very weak hint of cosmic birefringence at a 2.4 sigma level. And I remember there was so much talk on Twitter about these results, and people were excited, but 2.4 sigma is not really that much. And so not everyone was convinced. But just to show you a bit more of how this works, you have that observed EB. The observed EB is pretty much, the observed EE minus BB rotated by alpha. And then you have the CMB EE minus BB rotated by beta. And you can see here you're just plotting these two different things into different colors. And you can see that lower multiples, you get a strong signal. So you can see that the red thing here, for example, is much, much stronger than the blue thing, which means that the power from the red one, which is the observed one, must come from the foreground polarization. So this means that there's a lot of foreground polarization at lower multiples. But for high multiples, the red lines here are pretty much the same as the blue lines, which means that there's very little foreground contribution here. And yeah, I will now show you how the observed EB looks like, the actual EB data. And that looks like this. Like, there is a lot of noise here, and so it's hard to see this with your eyes, but you do see that there is positive EB for sure. And you can maybe, for example, in this plot, you can see that there is positive miscalibration angle, because you see a lot of, you can see some positive EB up here, which must have been rotated by a positive miscalibration angle. Yeah, but it is very hard to see with your eyes because it's just a 2.4 sigma at this point. Yes, and I remember the initial response, as I said, when this came out, people were excited, but 2.4 sigma isn't that much. And I remember that at the time, they hadn't really put the EB of the foreground into the analysis. They had argued that Planck has observed positive TB from dust, which means that there should be positive EB from the dust. And that's a good thing for this analysis, because that would mean that if there is positive EB from dust, that would increase the signal. But they didn't, in this analysis, they didn't put in a template for the EB of the foreground or try to model it in any way. And people were skeptical of that. So yeah, so after this paper came out, I came on board and we wrote a new paper where we looked at Planck data release 4 rather than 3. And Planck data release 4 has higher signal to noise. And so by excluding dust, doing exactly the same thing as Minami and Komatsu had done, we found this value right here, which slightly increased the statistical significance. And we tried to also account for the EB of dust by using a dust model created by dust experts, but the approach is also very generic. And the idea is to take the EB divided by EE of dust polarization to be proportional to TB divided by TE, because TB and TE and EE of dust has been measured, but not the EB. So yeah, we needed to use this model. And by using this dust model, we actually increased our measurement of cosmic birefringence to above 3 sigma. And this is also the mask that we use. So this basically tells you, the blue part here is the part of the sky that you neglect in the analysis. And there's a very strong polarized signal from the center of a galaxy. So we remove that from our analysis. And also like point sources that are linear polarized that we also exclude from our analysis. So we only look at the red parts of the sky here. So I'll mention a bit more about Ebio Dust, because that is it's important in this kind of analysis. So as I said, the Ebio Dust should be proportional to the EE of dust times TB divided by T of dust. And all these things have to be measured by the Planck satellite, but the Ebio Dust was not. And this is also a very generic approach. You just take the ALM indices and you play around with them. So more explicitly, we used an ansatz that was motivated by the works of Clark et al. And the idea is that, so this is pretty much the same equation that I'll show you guys with a proportionality constant AL. And then you have some kind of angle here, which tells you how misaligned the dust filaments in the sky are with local magnetic fields. I'm not going to go through into detail about this, but we then calculated this dust angle from the 353 gigahertz channels. We calculated this angle and we used this angle for all the other frequencies. And then we also fit for these AL parameters in 4 albins simultaneously with beta and alpha. So we're measuring these parameters at the same time. Yes, and as I mentioned, that by adding that model, we increased the statistical significance of our beta measurement. And then we released the paper. But then another question is that what happens if we include all the Planck data? Because in the analysis that I mentioned so far, we only looked at the HFI, which is the high frequency instruments of Planck. And the high frequency instruments of Planck are the 100, 143, 217, 303 gigahertz. And they are all, the foreground there are all dominated by thermal dust. And then the question is, what happens if you add the low frequency instruments of Planck? They have more noise, but they're not dominated by dust, they're dominated by synchrotron instead. And synchrotron has not been found to contain any EB at all. And there's no one has predicted it to contain an EB. So it'll be very interesting to see what happens if you measure cosmic birefringence by looking at synchrotron dominated maps. And then another question we asked was, what is the origin of this signal? If it is a real signal, what is the origin of it? And as I talked about in the beginning, I talked about Axions, because Axions will predict a frequency independent signal. So if we model the cosmic birefringence angle to be proportional to frequency to the power of n, then n will be 0 for axion-like fields, while for Faraday rotation caused by magnetic fields, it will be, this n will be -2. And then you also have other like crazy theories that will predict different integer values for n here. So the idea is then to sample this for beta naught and n to see what the frequency dependence is. And so we did that in a follow-up work. And this is, this is our results. We tried a couple of different things here. So the y-axis here is the cosmic birefringence angle, and the x-axis are the different frequency channels that we looked at. The black lines here, for the black lines or the black dots, we measure it individually for each frequency channel, and these are the black lines that you see here. We also try to sample this equation that I mentioned, where you sample beta naught and n, and then you get this gray 1 sigma band here, which is perfectly consistent with frequency independent, and it also rules out Faraday rotation causing magnetic fields. Because if this is a real signal, then this will be, I would say, the not exciting reason why we're measuring this. But yeah, as I said, it's consistent with being frequency independent, which is good news for Axon-like fields. And we also notice that if we assume it's frequency independent, we get this signal. And so by adding the LFI, the statistical significance increased once again, and now we're at 3.3 sigma. So as I mentioned, LFI is dominated by synchrotron, which has not been found to contain any EB. And so we kind of ignored EB in the analysis. And by adding that to analysis, we increased the significance of beta once more. Yes, adding LFI increased significance, even though, and we know that LFI contains little to no dust, and so this is very exciting. So the next natural step will be to add even more data, and so we also added WMAP to this, and then so what happens then? So we added WMAP that made the error bars slightly smaller, and this is the value that we find for that analysis, and that's the baseline value for this talk. And I just want to show you how this kind of also looks like. Here I have plotted the stacked observed EB power spectrum. So you're taking the inverse variance weighted average of all the observed EB power spectrums of all the maps, all the Planck and WMAP maps, and this is what you get. And what is clear is that you do see the acoustic peaks here. That there's no doubt about that. You are measuring something here. And so the question is, are you then measuring cosmic birefringence, or are you measuring miscalibration angles? But there is certainly, you do certainly see the EE peaks in this EB plot. So we then ran our model, we ran our analysis, measured all the miscalibration angles and cosmic birefringence angle, and this is how that model fits to the data. So you can see that this model, our analysis says that this signal is due to cosmic birefringence, as you can see by the EE power spectrum here, rotated by this value. And you can also see that the contribution in this plot. We're looking at 22 different miscalibration angles. We're looking at many different maps, and so by looking at so many different frequency channels, the miscalibration angle cancels because we're looking at so many of them. And that's why the contribution on the miscalibration angle is very small here. And when we then, when we fit this model, we find that the residual is very consistent with 0. The model fits the data very well. And so I've only talked about this full sky measurement, or nearly full sky measurement, the cosmic birefringence. We also tried a much bigger mask than this. So we tried something that looks more like this. As I said, we are neglecting the blue part of this mask. And by doing the same kind of analysis, we measure the same value, but with bigger error bars, as would be expected since you are looking at less data. But the point is that by using a bigger mask, we measure the same value for beta. And also, I haven't really talked that much about Dust EB because Dust EB does matter, and especially for larger masks like this. But with the Dust EB model that I mentioned earlier, we are able to recover the same value up here. If you had neglected that Dust EB model, then we will get something that's much, much lower. But we know that there is a lot of Dust EB for larger masks like this, and so that's why we get, so we get back, we get the value that we get for nearly full sky measurement. Yes, and then I also wanted to show you how the miscalibration angles look like, because we're fitting 22 different miscalibration angles at the same time here. There's 8 for the HFI, and there's 4 for the LFI, 10 from WMAP, because there's so many different channels. And you can see that they all cancel out. Some of these are not consistent with 0, but if you look at them totally and together, you see that they cancel each other out, as I showed in the EB plot earlier. While the cosmic birefringence angle is not consistent with 0 here. And this is the beauty of adding independent data sets, because if you have systematic problems with one of the data sets, it should be canceled out by adding more data. Yes, so I'm getting close to the end here. So that's the current status. We're now at a 3.6 sigma, and we have a much better understanding of the Dust EB, and we take it into account. We get the same measurements no matter what part of the sky we look at, which is very, very promising for this work. And I've also been asked a couple of questions. I'm going to do a very quick FAQ here. So when will the statistical significance improve or worsen? And the answer to that is we need better data, because at this time we have squeezed out all the data from Planck and WMAP, and we don't really have much more to go on. And so we're hoping that ground-based telescopes will start pursuing this as well. And if ground-based telescopes especially can calibrate their instruments well and guarantee that the miscalibration angle is small, then this analysis will be so much simpler, because you don't have to worry about the polarization of the foreground. You can just So and I think Bicep 3 had a very interesting paper that came out a week or 2 ago, where they said that they can guarantee the miscalibration angle to be negligible compared to 0.3 degrees. And so it would be, I think, I'm excited for a result paper from Bicep 3 within a year or something. And if they find a hint of this, then that would be so much fun. That would be so exciting. Yeah, so we are waiting for ground-based telescopes to pursue this. And are ultralight axons the best explanation for this? That I can't really say. What I can say, though, is that we measure the signal to be frequency independent. And so far, the only theory that I have seen that predicts the frequency independent signal are ultralight axions coupled to electromagnetism. So if you have any other theories that will predict little to no frequency independence, then that could also be valid. But I think ultralight axions are the most likely one if this is a real signal. So yeah, I've been working on this for almost 2 years now, and it's been a very fun journey, because the more data we add, the better we understand the foreground, the polarization of the foreground, the more promising this looks. And it's been a lot of fun. And one thing I haven't really talked about at all is that we also, in our early collaborations, we looked at instrumental systematics that could ruin this. And one of my collaborators, Patricia Diego Palazuelos, she looked at this and she found no evidence of instrumental systematics that could ruin this. And so that's promising. And the signal is consistent with being frequency independent, which is good news for axion-like fields. Yes, I think that's all I have. Thank you.
Thank you, Johannes, for a really interesting talk. Do we have questions from the audience? Yeah, I see a question from Junsa.
Hi, thanks for the very interesting talk. And it was good to know that by measuring the polarization of CMB, you can learn about the information on dark sector. It was really fascinating. So during your talk, as far as I remember, you assumed that you have no parity odd physics in the initial condition of our universe. And in this conclusion, you also say that as long as you have a frequency independency, then that means you can safely say that axion-like fields are most likely. And I just wonder if what if the initial condition of our universe had initial parity odd physics, would that also end up in frequency dependent rotation angle?
So, so you're talking about inflation here, right? If there's parity violation?
Yes.
Yeah, that's a good question. But the light that we are looking at was emitted 400,000 years after inflation, and we are finding that it has rotated since then. And so I would say no. And also, as I showed, these things, what you do see here are the intrinsic EE power spectrum of the CMB that have been rotated after the CMB into EB. And so I do not think that this is connected to parity violation during inflation, I would say. Maybe there's a mechanism that connects the two, but I would say they seem to be disconnected things.
Okay, then is there a way that we can say about the initial stage of the universe, or if there were parity odd physics or not, but with this statistics? Because I guess so from the observed power spectra of T and E, or B and E, something like that, we are combining two results, which could be coming from the path from the CMB to our position, and another part will be the initial setup of our universe. How can we discern between the two?
Sorry, wait, can you say that one more time?
So I guess the signal we are looking at could be a combined result. One part from the initial some exotic physics, like having initial parity odd physics in the inflation era, and the other part could be axion field between us and the CMB, last scattering surface. Is my understanding correct? So I thought the observed signal could be resulting from both sides, but in this case, we are assuming that initial parity odd physics is negligible. Is that correct?
Yeah, because as I mentioned, let's see if I have it there. The equation I've showed earlier here, we set the EB of the CMB to 0. So when the CMB was created, we assumed that there was no parity violation at all. And I know that there have been works. There was a recent paper out that basically tried to say, what if the signal we're seeing is not caused by birefringence, but is due to this thing? And they did not find that to make sense. They found that if that was the case, that if this were non-zero during CMB, then we should have observed a BB power spectrum that was larger than what has been constrained so far. So I don't really see a way to connect this with the
inflationary physics.
Yeah, I don't see a way to do that, like parity violation during inflation.
Okay.
But there are, of course, interesting research on exactly that with parity violation, the 4-point correlations of galaxies and stuff. So I have been thinking about this, but I don't really see a way to connect the two.
Okay, thanks.
Even though both are parity violating physics. Yeah, thanks.
Okay. Thanks.
Right. Next from Jovi.
Hi, can you hear me?
Yeah, I can hear you.
Yeah, very interesting talk. Thank you. I have a couple of questions. So this slide, you write down CLEE observed and CLEE CMB, right? What do you mean by CLEE CMB?
So this is just what the predicted lambda CDM EE power spectrum. So what in our analysis we just take CAM or class and we calculate the EE power spectrum based on the lambda CDM best fitting parameters.
So the theoretical one.
Yeah, the theoretical one. Yeah. So that's yeah. So we use a Boltzmann equation solver.
Oh, okay, okay. And you mentioned that you improved the significance from 2.4 sigma to 3.6 sigma by using data with less noise.
So in the original analysis by Yutu and Minami 2 years ago, they looked at the Planck data release 3, and they only looked at the HFI. So maybe I can. Yeah, so for the Planck analysis, they only looked at these 4 here. And they used Planck data release 3, while we use Planck data release 4. And Planck data release 4 has less noise, and I made the error bar smaller. And we also added the LFI, which are these 3 data points as well. And then we also added WMAP. So we added more data. And in addition, we also had a model for the Ebio Dust, and that also slightly increased the measurements.
So, like, do you have an idea of how much of an improvement in signal to noise there is going from release 3 to release 4?
These, I think, yeah, let's see if I have the numbers. Yeah, so this was on original analysis, just PR3, Planck data release 3. We used PR4, and this error bar went from 14 to 10, 0.10. No, 11. No, sorry, 11. 0.14 to 0.11.
Okay. I have one more question, if I may. Okay. Is there a prediction for the cosmic birefringence angle from ultralight axons theory? Not just frequency dependence.
So that's a good question. So if there are these ultralight axion fields, I have to go far back. Yeah, and the mass is in this range. Then the field today is in its vacuum expectation value, which is 0. Then it only depends on the Kaplan constant times the value at the CMB, the emission time. And I think that within the axion-like field of physics, there's a lot of different sub-theories. And so I don't think I should say anything about that. I don't think I'm qualified to, but I don't think there's one prediction. There could be many.
So more like a free parameter.
Yeah.
Okay.
But some of them are also more specific. Yeah.
Okay. Thank you.
Thanks.
Right. Arman has a question as well.
Thank you so much, Johannes, for the nice, interesting, also provocative talk. Okay, the claim is big, right? I mean, basically saying that this cannot be seen in the, there's no systematics, not observational effect. But as you know, the community have been taking it, with so much care, right? I mean, so people, yeah, I mean, it looks like that people cannot find what is going on here, but at the same time, you are claiming that this seems to be there, and even the significance of the signal seems to be increasing now. It's more than 3 sigma. So what is the next step? Okay, so is there, I mean, any way to make things more clear? I mean, for example, you showed this frequency-related band. So if you show that again, I can see that 217 from Planck and So is there any other way that we can make this uncertainty tighter and make it better? So
Yeah.
what is the step, right? So at the moment, results are
Yeah.
there. It's already significant, but people are cautious to take it.
Yeah. Okay. Yeah. So that's a good question. So for example, if you look at the official Planck results themselves, if they could guarantee the miscalibration angle to be 0, you already have a 6 sigma detection here. But they can't guarantee that. And so I think that we have done everything that we can with the Planck data, and I think this is now left into future experiments' hands. And the best way to do this is just to really, really tighten your miscalibration angles, really make them small as you can. If you can make them negligible, then you will have, if Planck had made this negligible, you have a 6 sigma detection of it. So that is what next experiments have to do. They have to make sure they can calibrate the instruments well.
Do we know that how well we can calibrate that, right? I mean, I agree with you that this looks like a 6 sigma, but since the reason they're not claiming is that, as you said, it's not very clear that what is the value of alpha, right?
Exactly.
And if you don't know that basically 6 sigma and 2 sigma may not be different.
Yeah, exactly. So we use in our analysis, as I mentioned, we use the foreground to calibrate alpha, figure out what alpha is.
Right.
And that's how we get to the 3.6 sigma result. But the best, but we were at the dead end pretty much at this point. And the next step is pretty much and as I mentioned, Bicep 3 has already said that they can guarantee this alpha to be negligible in their for their experiment. And so I do hope that within a year they will maybe have hopeful results or results that kind of go.
So I mean that even with the Bicep or KEK, you might get some very tight estimation of alpha, which basically then
they have very tight constraints on alpha, and so they don't have to worry about the polarization of the foreground at all. They can just look at the CMB. And so that analysis is much more straightforward.
Okay, and another question is related to what Joby asked. So this looked like this Axion field can predict such a behavior, but you at the same time saying that, look, but they can behave in a very different ways, right? I mean, they can, so there is no particular prediction that this model can have. So what would be the outcome of all this? That we need axions, or that's one of the options, or is there any other theoretical model which can predict such a thing?
So the only model that I'm aware of are axioms. That's the only one I'm looking at. So I can't really say much more than that. But if you do prove that this signal is real, then you can start, and then you can start wondering if there are axioms, what more would you expect from such a signal?
Have you looked at it, if this is, for example, real, and it is really your beta value is, let's say, 0.30, right? Then can you then, and if it is coming from the axioms, can you then come with some estimates on the properties of this field?
So you can't really, you can, so
let's say that observationally we prove that, okay, beta is 0.3.
Yeah, so that means that you can then constrain the product of the emission time field and the coupling constant. So you can't really break those two apart. And you can also say that the mass has to be within this this range. So you can learn these small things, but not much more than that.
But still, that would be
big. So, yeah.
Okay, thanks so much.
Yeah,
good luck. And one more. Okay, this is more like a. Do you or Eiichiro really think that this is there, or you just think of it as a exciting things to pursue?
I think that asking the personal opinion of a physicist is always scary, but it's like the more I've worked on it, the more optimistic it looks, and it hasn't gone away. If it is a statistical fluke, you expect the 2.4 sigma to go away, but it hasn't. We added more data, independent data set, and it increased. So I don't know, but it's fun, it's exciting. But I think if a new experiment, a new team were to do this on new data and they also find something, then maybe I will start being maybe then
Okay,
I'll-
thank you. Yeah, thanks so much.
Yeah, thanks.
Right, sorry, Joby. May I ask some questions myself before I had quite a few as well. So yeah, just first, I wanted to ask this over 3 sigma. I was wondering if this beta angle, since it goes in the estimation process as this cosine of 2 beta, for small angles it'll be something like 1 minus beta squared. So I was just wondering if the expected distribution of this beta estimate itself follows Gaussian distribution, because otherwise the 3 sigma wouldn't immediately correspond to p-value of like 0.01 as we normally think. So yeah, I was just wondering if you have checked if beta follows the Gaussian distribution.
So if beta, so our value of beta isn't Gaussian because we get asymmetric error bars. Yeah, but that's very, very, very slightly though, very slightly. Let's see. Yeah, as you see here, it's not symmetric error bars, so they are slightly different. But
right, when you say the significance, you divided the lower error bar.
Oh, okay, yeah. Okay, so to calculate the statistical significance, so I'd use a Monte Carlo metropolitan sampler. So we have a bunch of samples, and we let that run for a very, very long time, and then we looked at, and we took all the data, tried to fit the curve that was skewed, and then we used that to calculate the statistical significance.
Right. So it comes from those samples.
Yeah. We also looked at the amount of samples that gave a negative beta compared to all samples. And so use different ways to make sure that the 3.6 sigma makes sense.
Right, that makes sense. Thank you. And one other thing is probably already checked in the systematics analysis, but would the anisotropic beam, like the point spread function of the effective beam, would that affect this measurement at all? Has that been checked?
Anisotropic beams were not checked. I think anisotropic beams are hard, so I'm not qualified to talk about that. So we haven't really ruled out all systematics. There could, of course, be unknown systematics here, and maybe asymmetric beams are. I don't know enough about them to say that, but we did look at like temperature to polarization leakage, or like all times of like polarization leakage, and we did look at we went through like simulations of the Planck data to see if there was anything in the pipeline that could bias beta, but we did not find that either.
Right, awesome. Yeah, I can't immediately think of a connection because it's beam is in spatial bias. So yeah, but I was just curious.
But it would be interesting to see if there could be a bias from that, for sure.
Right. Yeah. And so one more thing before Jovi's question, maybe. This part where you change the mask, actually you're just showing here, it was really interesting that the error bars don't seem to change too much, even if you reduce the sky fraction, which made me wonder. Yeah.
For the beta?
Sorry? Yes, for beta, yeah.
Yeah.
Yeah, so for larger sky mask, you got like still like a decent constraint on beta. So I was wondering if you do some kind of analysis where you split the available sky into like say 2 halves, and then compare the estimates of beta from those parts, would there be a good consistency check?
Yeah, you are right about that. We did many checks on different masks, and we didn't do the one you just mentioned, but we did check many masks, and we do find that it does seem to be consistent. It does lower a bit for some masks, this value, but it is still consistent with these values, I would say. But yeah, but you're right. I haven't made the check where you divide it into upper and lower mask.
So I was just curious.
Yeah.
So should we still have a question?
Yeah, so pardon me if this is a silly question, I'm not very sure about it, but If it is really due to axioms, then would we expect to see a signal in the reionization photons as well?
That is a good question, and I think that depends on the mass of the axions. Yes, and I know there have been papers on this, and I should know what their findings are, but I'm forgetting that right now. But if the mass is a bit heavier, like 10 to the power minus 28, that means that the rotation would have happened before reionization. While if the mass are lighter, then the rotation would happen after reionization. So you can look at the EB power spectrum to see if there's a reionization bump or not. And that could be like a natural next step if the signal is real, to try to figure out what the mass would be.
So that could be used to constrain the axion models?
Certainly the mass, for sure. Yeah.
Okay. Oh, thank you.
Yeah, thanks.
Right. So if I may ask one final question. So on slide 28, you showed when you're studying this frequency dependence, you do measure this n is still to be slightly less than 0. Of course, it's within the error bars, but do you think this is just a coincidence, or can you think of some reasons to maybe why the data prefer like n slightly less than 0?
Since it's within half a sigma, I wouldn't read too much into it. That's I think this is perfectly consistent with 0, and so I'm not reading too much into that. But of course, I mean, I could be wrong. There could be a very slight decay in beta that is not well compared to a power law model like this. That could be the case. But yeah.
Right. So that makes sense. Cool. So are there any other questions? Since it's 5 p.m., let's conclude the seminar.